Okay, thank you. I'm really honored to be here. I had a very good, intense day, began early, and I visited and I talked to many students, high school, and I'm glad to be talking to you in this beautiful university where a lot of work is done in climate as well. Science and impact of climate change, that is what I will be talking about. I will mention at the beginning a little bit about, you're hearing me okay, right, I presume? At the end too. About weather, but very briefly. I don't want to give the impression that weather is here and climate is there and they're completely separated. They are part of a complicated system, which is what the atmosphere is. Okay, first of all, the definition of weather and climate. Weather is the state of the atmosphere at a given place at a given time. Climate is an average in some sense, which is an intuitive sense, but in addition to being an average of various quantities, whether temperature or winds, climate also has information concerning the frequency of occurrence of things. How often hurricanes take place, how often floods take place. So it is an average as well as information concerning the probability of certain things happening. We are all familiar with the fact that the weather is changing all the time. That is we have every day. But both weather and climate have been changing on many different time scales since the beginning. We are referring to this continuing changing of climate, say, as a natural variability, the fact that these fluctuations are taking place all the time. If it is just natural variability, these fluctuations of things, these changes, take place about a mean that is always more or less constant. But if these fluctuations change about something which increases or decreases with time, then we're talking about climate change. We have changes in temperature, but the average temperature has been slowly increasing as a function of time, certainly since the beginning of the Industrial Revolution. So climate change means fluctuations, but about a mean that grows as a function of time. So in general, and I will also show you some changes which are drastic, not slow. And I will be, in general you can say that any signal has a random change, a random fluctuations, as well as a deterministic component. Variability of day-to-day weather, is known to each of us. But what the next few graphs will show how important it is to have accurate prediction, both in terms of lives and property. Just a few graphs. As I said at the beginning, I just cannot ignore weather and just talk about climate. In last year, things were particularly difficult. It was a very difficult year. We had 1,000 lives that were lost in the United States, which was about twice the average of previous years. The National Oceanic Atmospheric Administration estimates that we had about 14 events of this kind, with more than 1 billion damages that occurred for each event. And that is the largest numbers that we know about since 1980, when we began putting together these statistics. The previous year where things were pretty bad was 2008. The average events of this kind since 1980 was about 3 to 4 a year. Collectively, in this period of time, the damages have been 55 billion. The smaller events, which did occur, which do create damage, but less than 1 billion per event, are not part of the statistics. I give you this example to point out how important it is to have good predictions. And I am contrasting the hurricanes, one hurricane, the Galveston Hurricane that took place in 1900, to the one, Katrina, that we're all familiar with in 2005. And the point here is that as far as the events are concerned, they were pretty much the same in terms of intensity, speed, the trajectory that they followed, and the intersection that they had with the coast. That is roughly the same. But look at the difference between what happened in 1900, where 10,000 people died out of a population of about 40,000 people. A quarter of the people died because of this hurricane. Katrina, I'm repeating, same type, same intensity, caused too many deaths, 1,800 fatalities, but out of a population of 1.5 million people. And the difference is that there was no weather prediction in 1900, there was no warning, therefore, whereas actually the prediction that was made for Katrina was very good. We should be proud of it. It could have been much worse. People died, true, but the predictions were very accurate. And so I think this is an important example that shows how essential it is for this country, or any country, to have a good prediction system. This is a specific example concerning hurricanes prediction. And what you have here is the Hurricane Isabel. And I will show you what was the prediction that was made when it took place in 2003 versus the prediction of the same hurricane 7 years later, simply using a more sophisticated prediction problem. In those 7 years, a lot of progress was made, and I want to show you the effect of this problem. This is 2003. You have a cone of uncertainty, that white cone that you see over there, and the projection as time evolved, which is the bigger cone. This is a classic prediction of hurricanes. You define, you predict the cone within which the hurricane moves, and you also predict the intersection that the hurricane has with the coast. All right, this is 2003. What I'm showing you now is this is the cone 7 years later, much smaller. That's the, I don't know, reddish something. And that is 7 years later. And then you can also see how much more accurate and smaller that is the intersection with the coast. These are the difference between 7 years of the performance of the prediction, and a lot of progress has been made, still not enough, in predicting the evolution of hurricanes. Okay, I told you, you may know weather changes on a time scale of weeks, days, and we're very familiar with it. But it changes at larger time scales. We are very familiar with the El Niño and La Niña atmospheric processes, phenomena that take place every 2-3 years, and there has been some progress made, not perfect, about prediction of these events. The purpose of showing you this view graph is to deal with the fact that prediction are not necessarily, events are not necessarily smooth. And this is the best example I know of, at least in more recent times, although this is 10,000 years ago, of drastic changes in climate, 15 degrees increase, that took place over a period of time of about a decade. So if we feel that we should not worry or we should not be concerned about climate change because it takes place over a period much longer than our lifetime, we should be concerned that things have happened in the past that took place over a much shorter time scale and very large. I'm not saying that it will happen, I'm not suggesting, I'm only making the point that it has happened, not necessarily knowing the reasons, but as in all cases of climate, sometimes we really don't know what actually goes on, and we should not have the presumption of knowing it either. The next set of data I show you is the changes in climate at much longer time scales, 100,000 and longer. And this is a view graph which shows you the entire history going back to 60 million years ago, when major changes in temperature took place, when continents were moving one with respect, colliding with each other, and when major amounts of CO2 were either emitted or absorbed. And it was the process of absorption by ocean, by the atmosphere, by the CO2 becoming petrified in the limestones. It transforms itself into limestones. So the CO2 decreased as a function of time somewhat drastically, and you see that curve over there. Then things settled down, and the decrease ups and down was reduced at different speed. Then you look at this place, which was about 5,000 millions of years. That is 5.3 million. The scale is right here, 65 millions up here. Then we go down and we look at 5.33 millions of years ago, and we amplify this, and that is what we see. CO2 continues to decay. The temperature continues to go down. As we go further, you can see some oscillations here, which are almost nice wave-like things. And then we take an amplifying process here. We amplify this area, and we see what happens in the last 500,000 years ago. And you see in this ups and downs, surely some regularity as well as some randomness. The distance between these peaks is not perfect, but you will believe it if I say that it's about 100,000 years ago. And superimposed to that, you will see some smaller fluctuations. In the end, what I will show you is that since 1750, the beginning of the Industrial Revolution, we are going to depart from this process. We are going to depart from this shape, and all of a sudden we will see a drastic increase in temperature on these time scales. I will spend a little time to explain where these oscillations come from. We don't know everything about climate, but we do understand some of the processes, and this is one of the things I want to show you. So I'm now going to look at the bottom part of the screen. Before doing that, let me spend a few words. Why do we study climate? We study climate because climate matters on quite a number of very important things, ranging from human health, food production, energy resources and use, economics, business activity. The daily business is affected by climate tremendously. Tourism, and in general recreation opportunities. So, climate matters. That's why we studied. Besides, many of us study climate to understand how the Earth works. It's nice to know how the planet in which we live works. But that aside, there are practical reasons. Our business is one in which the science is important, is interesting, but in addition has a lot of applications. And that makes a challenging field for many of us. Okay, climate matters, I just said that list continues. It matters on natural processes because it may affect the formation of storms and hurricanes and their intensity. It may affect droughts, floods, sea level, and if you're living in areas where, and I will have a picture, close to the sea or at the sea and you don't have much, you don't tolerate much change of sea level, you have a problem, and of course it affects air quality. Excuse me, I did not look at the time I began, but if you can give me a signal when I have 5 minutes left, I really appreciate it. Policy decision. There are a lot of issues concerning environmental regulations. And as we have a debate these days, or weeks, the presidential debates, although I regret to say that climate has disappeared from the political debate, and each of us can give its own reasons, I have my own, nevertheless, there are always expressed concern about environmental regulations that some believe is the beginning of all our problems. And so, but it is true that environmental regulations are needed if we want to do something about climate and needed to deal with this effect of human activities. There are issues of national security. I personally read some reports that have been written by the Department of Defense that deals with the water availability and distribution of water. There are countries in areas, in particular areas, which are strongly affected by the availability of water. And, you know, to the extent that we have to be involved, we should be very aware of the impact of this. And then there is an issue of technology investments, which are extremely important in a variety of ways, but if you think about just ways of minimizing the use of energy by having optimization of systems that we use, or discovering and producing alternative sources of energy from wind, etc. So that implies certain policy decisions that mean investments, and you don't expect all the investments to come from the private sector. And there are many areas where initial investment by the government were followed by private sector investment. There are international relations, I mentioned it earlier, but there are questions of the importance of water, of the affluent versus the poorer nations. There is competition for national resources. We have used a lot of processes that have produced a lot of CO2. And it's not clear that it is fair now for us to underdeveloped countries or the countries that are developing to have the possibility of doing what we've done. And so there are a lot of international issues that are involved with climate change. How do we study climate and climate change? I take the time to tell you a little what we do, primarily for those of you who are students, and I think I like to make sure that study climate means to get involved in a variety of things. On one hand, you may be interested in designing a system to make the measurements, distributing system of measurements across the land, or designing satellite missions. Satellites, of course, have the advantage that by taking a global view, they provide a lot of global information. Climate is a global phenomenon, it's not a local phenomenon. You will be able to interact if you are in certain places such as Goddard Space Flight Center and other centers of NASA and the National Oceanic Atmospheric Administration. You, as a scientist, will be able to interact with projects and managers that build the mission, build the aircraft, build the instruments. And if you like to do that, you can do that. And that interaction means that you can provide the engineers information which is essential. You may design the instrument, but in fact, when the instrument is being built, 99% of the time they find out they don't have enough money. And so they will come to the scientist and they say, look, we don't have the money to build the full instrument. Can you accept a degraded version? And you as a scientist have a responsibility to determine and provide information, because if the instrument is degraded too much to save money, it becomes worthless. There are issues of looking at the data. This is not a small issue. The data are dispersed, are not regularly distributed. And when you analyze the data, you better do it carefully. These are global data. And there are areas such as North America where there are plenty of data. But there are areas in the rest of the world where the data are not are dispersed in a strange way. And when you are claiming that you are producing information concerning the global average, you must do it right. And there are a lot of challenges in doing that. Then you may, you get a lot of data, you may be involved in the display of the data. That is important too, because the ability that we now have to display data on computers, you really have to accept the fact that we learn a lot by just looking at the data displayed on the computer. You just learn how the system works. And then there is issues of modeling. You can do a lot of work in numerically representing how the system works. You as the computers, I think the weather prediction was the main reason that the computers evolved as quickly as they did and as forcefully as they did. I think, no question in my mind, the first computer, the first very big computer was located at the National Center for Atmospheric Research in Boulder. And it was a huge computer. Now probably would have the dimension of my computer. But at that time, the motivation was weather prediction because it takes a lot of computational resources. Improving the time resolution, improving the spatial resolution of the programs. And so you really have opportunities if that is what you decide to do it. So I just gave you some example of the variety of things that you can do in this field that might be attractive to you, other than just, you learn about the climate, which is in itself a satisfactory objective. Okay. There are basically 4 questions about climate change. First of all, is climate changing and why? Secondly, are we responsible for it or we contributed to it? Third, what is the impact of these changes? And fourth, what do you expect the changes to be in the rest of the century? With respect to the first one, the answer, these questions are not simple. The questions are not simple because the atmosphere, and we often refer to as the Earth system, is made of many components. The atmosphere, the biosphere, the cryosphere, that is the polar regions, the hydrosphere, oceans, water, and finally the solid portion of the Earth's surface, the ground, and therefore the biosphere associated with it. And these components are not living independent of each other. One of the problems that makes the system complicated is that we would not have El Niño if we only had the atmosphere or the ocean. The El Niño is the result of the 2 pieces interacting with each other, and so is La Niña. So you have a system that is made of 5 major different components interacting with each other. And furthermore, the Earth is a planet, and it's not the only planet. And so we have other planets at different distances from the Earth, and specifically, because of their closeness, Jupiter, Saturn, and Venus, which are interacting with what we do, with our motion. And I will give you some explanations shortly. Let me repeat, the Earth is part of a complex system. It's a complex system itself, but it's part of a system that has other planets, and therefore the motion of the Earth is affected by the presence of the other planets. It's affected in a small way, but in a fundamental way that affects climate. And I hope I will convince you of that in case you are doubting. And finally, climate depends on the solar intensity. And the solar intensity, as well as where it points, is an important piece of the information. It so happens that in the last 200 or so years, the changes in intensity has taken place, but it's not considered to be an explanation for the changes in temperature that we have had. Climate change is a global phenomenon. I said that earlier, and as I said also too earlier, it changes all time scales. What? Okay, I will come back to the third bullet. It's okay. And the point I'm going to make, and I will make it, is that the effect of the climate change is produced by, I believe, human activities, and the amount of this human activity is strong enough to affect what would be naturally happening. So that is, the changes, the natural changes independent of humans, are caused by certain processes, which I will mention in a minute, that are of the same intensity as humans. In other words, we are effectively competing with the natural processes, i.e. we are forcing the system, we are putting heating sources into the system that are similar to those that produce the changes in climate. The other thing that we must remember is the greenhouse gases that we put into the system don't stay there for a week. They can be there for centuries. So, and the changes that are produced by greenhouse gases produce changes both on the land and the sea surface, and they take place slowly. We are looking at processes that don't take place in 1 week, very slow processes. And it is the slowness of these processes that adds another component to global change, and then it is an emotional component, if you wish, because it's one of those rare cases where what we do today is going to affect our kids, grandchild, etc., because what we do today is going to stay there for centuries. And so it's something that is unique of this field. Is climate change underway? Okay, and I will show you yes, but I will also show you that the example I will give you go beyond what is the regular variability. Okay. This is the diagram that I showed you before, so I'm not going to spend more time, but it simply confirms what I said, that we had major changes of temperature on the vertical axis to the left, and you can see when ice began to form in the Antarctic ice sheet about 40 millions of years ago, and in the northern hemisphere about 10 or so millions years ago. So here you have a picture of the changes, major changes in climate. Here you have another picture of changes in temperature, average temperature, only since 1750, which, as I mentioned, is considered to be the beginning of the Industrial Revolution. And you can see there the average temperature global on the left axis in centigrades, and what you see there, very nicely, I think, the big, huge effect of volcanic explosion. A typical volcanic explosion effect doesn't last very long. The Pinatubo was modeled by Jim Henson at this in New York, and the estimate was that the effect of such an explosion was lasted for about 2 years, because eventually what goes into the atmosphere during explosions gets absorbed, gets dissipated, and disappear. But I thought this was a nice picture. This is a picture coming from different models, and that is a different data interpretation that begins in 1860 and goes all the way to something after, just a year or two ago. And it's a difference between the temperature that we have at a given time and the average value from 1961 to 1990. It is very often useful to represent not the temperature itself, rather the difference between that temperature and some average of reference. And the reason is that when you if you were to plot just the temperature, you may have an unusual amount of noise into the system, because in going from A to B, you cross a forest, you might have certain things happening that make the changes in temperature relatively large, but when you're talking about an average, that is what you see. So you average out the noise by taking the difference in temperature. Do you have any doubts about the mean sea level change? Here it is, in millimeters on the vertical axis, and as a function of time since 1880. And you have different rate of changes due to a variety of reasons, but primarily variations in temperature as well, and therefore primarily in the amount of ice that melts and gets into the water. You have a disappearing Arctic sea ice, which is a very important phenomenon that I come to it. And you have here the story. And one of the things of great concern about this diagram, totally unpredicted. Nobody predicted that this would have been the evolution of the Arctic sea ice as a function of time. This is a plot from 1950. And this, in the vertical, you have the sea ice extent in millions of square kilometers. Another picture here deals with the same issue. On the left, you have the sea ice extent. You see that white part, that's the sea ice that covers is the ice that covers the sea, and in pink or whatever other color, you have the value that was the average amount of sea ice that was referring to the period from 1979 to 2000. This area is clearly smaller than this area. And on the right, you have the amount of ice concentration. Again, you have smaller amounts compared to what it was before. The next slide is a beauty. It is the Himalayan glacier as it looked in 1968, not 2 centuries ago, versus 2007. And I could show similar things in Europe, South America, China. This I thought I happened to find it a very attractive picture. We have the only satellite missions that has no active sensors is the Gravity Satellite Ice Sheet Mass Measurement, otherwise called GRACE, a nice name, whereby you have 2 satellites moving together, one follows the other, and each senses the mass of ice underneath. And depending upon the relative position of the 2 satellites, they might change the distance between the 2 of them. And so what is being measured here is simply the distance between the 2 satellites. I'm repeating, these 2 satellites move together, but they have slight variations of the distance between the 2 of them, which provides essential information to the mass of ice about which they move. The ice is on the ground, the 2 satellites in space, they move, they do this, and through a rather sophisticated algorithm, they can infer the position of ice and the amounts. And that is what these things provide. These are the Greenland ice sheets in mass, in gigatons, as a function of time. In the Greenland ice sheet here and the Antarctic ice sheet, and both of them clearly indicate that the amount of ice is decreasing. No, I hope it's clear that no matter which variable you consider, they are all together consistent, each variable change, with the idea that the Earth is warming. It's not just the temperature, it's the temperature, it's the ice mass, etc., all consistent with this processing. And what causes climate change? Climate change is caused by the fact that there is an energy imbalance. More heat comes in than goes out. More energy from the sun comes in than it goes out. If the system were in balance, you would have the same amount of incident. If you look at the sun, this is the amount of watts per meter square. Remember, a watt, your bulb is typically 60 watts. Okay, you look at the sun, you find that what would come in is about 1367 watts per meter square of the Earth. Which means that that is total amount that comes in. Excuse me. Now, what happens here is now you imagine the Earth to be divided in small meter square areas, and that means that the incident of energy from the sun is about 342 watts per meter square. If the system is in equilibrium, some of this energy is radiated back from the ground, and some of this is reflected simply and directly from clouds and other particles in the atmosphere. But the sum of the one reflected directly by clouds, aerosol, and the one due to the ground that reaches a certain temperature, so it radiates, the ground itself, the sum of the two are equal. But if, on the other hand, we are not in equilibrium, then this is the picture that you end up with. At the top, you have the balance I just showed in the previous slide. But at the bottom, this is what comes in, as in the previous slide. But what comes out is this piece. There is a missing, which is barely visible on the screen, a yellow piece. This difference is what causes the warming of the Earth. atmosphere, ocean, the Earth system. The amount of energy that goes out is not the same as the amount of energy that comes in. Here is a picture that gives you some more explanation about the physical processes that are taking place. The energy coming in is this one, 342 watts per meter square. Some of it is reflected by clouds, and sure enough, it goes back out. Some of it goes down towards the ground, and as it approaches the ground, a component goes directly reflected by the ground. If there is ice, it just hits the ice and goes back, leaves nothing behind, and it goes back out to join the other piece. On the other hand, what actually gets into the ground, gets absorbed by the ground, hits the ground, the temperature of the ground goes up, and therefore any body that has a certain temperature radiates, and therefore the ground sends the radiation out towards the space, and here it is in this description, and that is goes up. This is energy emitted by the ground, it goes up, and the little portions of it goes through, whether there are clouds or whether there are trace gases. But if there are the greenhouse gases, these particles of fluorocarbons that are in there, CO2, etc., CO2 primarily, methane, that absorbs, I should say, and re-emits energy towards the ground. So in the presence of what we call greenhouse gases, the energy emitted by the ground does not go into space. It gets interacted with by the greenhouse gases that tends to prevent that energy from going down. The bottom line is that this is what goes out. And the bottom line is this piece plus this piece is not the same as this one. This piece of energy coming from above is larger than the sum of these two. And as I indicated, what does it? The clouds do it. The ability of the ground to reflect does it. If the ground is covered by ice, the energy gets reflected very effectively. If it is a forest, it's not the same. If there is water, it's not the same. And then finally we have some processes such as convection. I don't want to go into it. But you have here the various processes that are responsible for the fact that the energy comes in from the sun, but not an equal amount goes out. And since I mentioned clouds, since I mentioned forest, or I should have, since I mentioned greenhouse gases, we, with our activities, are affecting these processes. If the Earth temperature goes up, there is more evaporation of water. Water is a very powerful greenhouse gas. Water is very effective. And you know that, because if you go in the mountains, for example, and in the evening the sky is clear, it's a beautiful scene. It's cold. It's cold, certainly colder than during the day. But if the same night you have cloudiness, the temperature is much warmer. You must have experienced that, whether you're a skier or not. The effect of water vapor is very strong. So clearly, if the Earth gets warmer, more water vapor is radiated, and therefore that process feeds back and increases the temperature. What causes an energy imbalance? Basically, the energy imbalance I just finished describing, most of it, not all of it, because it's caused by changes in the incoming solar radiation. And I told you that this can happen because of solar brightness changing, and I told you earlier that's not particularly important, but more important is changes in the orbit parameters, which I will mention in a second. It changes in greenhouse gases, cloud cover, aerosols, surface albedo, the ability of the surface to reflect energy, and it changes in natural variability. Okay, now we come to the question, are we responsible for it? This is the same picture that I showed you earlier. And so now I'm going to look at the bottom panel. before I do that, I thought you might see a lot of information comes from looking at ice cores. A lot of information concerning temperature structure variations in the past thousands of years came when we succeeded in drilling holes in the ice and extracting the ice from them. And this is a picture we are talking about, basically cylinders of this size, and that means that we have been able to go and look inside this ice, and when the ice formed, it trapped gases that were there at the time the ice was formed. And through a rather complicated, sophisticated, and imperfect process, we have been able to infer temperature as well as gas structure as a function of time, way back hundreds of thousands of years earlier. This is a picture of the last 500,000 years. At the top, you have the global temperature. Second, think of the second just as a greenhouse gases. Surface albedo, reflections of energy by the surface. And finally, sea level. And I think it's very clear, I hope it's very clear, that indeed these four traces have some coherence as well as some randomness, but they are also, you can see, they could overlap with each other. And so these processes are not unrelated to each other, are connected. And I have more evidence of that if I go to consider CO2, methane, sea level, top panel, surface albedo and greenhouse gases, I already said it, the middle panel. And the final one at the bottom is the observations of temperature as well as some sophisticated models that are interpretation of this temperature that are reproducing the two traces very well. So we have a structure which is not totally random, and it has some organization. So why do we have that? And here is the answer. We have that because, as I said earlier, the Earth is in the presence of other planets, Venus, Jupiter, etc. It senses their existence, and as a result of that, over long time scales, the Earth does not go through the same characteristic orbits, but there are small changes. You see the elliptic will slightly change. The eccentricity, as it's called, varies. And the period of this variation is listed here. When the axis of rotation, the axis of rotation is not constant, it varies gently. And here is the depiction. And that change in rotation, as well as in inclination, is called tilt, when it talks about the inclination of the axis of inclination, and the speed of rotation around that axis is called precession. And in white, you have the characteristic periods that are characterizing these changes. Small changes over long period of time, but they are there. And it is the merit of a fellow by the name of Milankovitch. This is his picture. This is his name. That has demonstrated analytically what was the result of the fact that the Earth was moving along a trajectory that was varying gently as a function of time. And you have the eccentricity plotted, you have the obliquity plotted, you have the precession plotted, and you have the total amount of the temperature variations, the bottom one, as a function of time. And I'm saying to you that these distances roughly are 100,000 years. The same time distance, I don't know if I have it here, no, the same, this explains the separation between these two. And I don't want to go back to an earlier slide, but you can, if you analyze carefully these signals, what shows up inevitably is something with this periodicity of 100,000, the strongest, 400,000, and then you will see, I won't see the 41,000 years periodicity rather well. So we have an explanation for what this natural variability that is rather convincing. By the way, it took a number of years for this theory to be accepted. It happens. and it took a century and a half for some years ago to accept the fact that the sun was not rotating around the earth. So let's accept the fact it took a few decades for this interpretation to be accepted. Okay, and this is what I was saying, is that the theory is that these variations are such that at 65 degree north, all right, at certain periods at the end of the summer there is no sea ice, or there is sea ice. So it is this slowly varying characteristic of the orbit is such that the amount of sun that reaches the 65 degree north can be such that you go from a period of heating to a period of cooling. What I've done here is not what I wanted to do. Here we go. The distance between this and this is 100,000, and it is the beginning of the heating or the cooling has to do whether or not at the latitude of 65 degrees at the end of the summer you have or you don't have that the Arctic sea ice present. And it is this transition which takes place over 100,000 years. It is this transition that causes these oscillations. Notice also that the heating is much faster than the cooling. We're talking about 10,000 to warm, 90,000 years to cool. It's a difference that we don't fully understand, but we should keep in mind that apparently the heating it is taking place much faster than the cooling. Okay, so you tell me, okay, so what? Well, all right, let's see what has happened since 1750. What you have here is the difference between the temperature and the average over 100 and some years of the temperature. And you see from 400,000 to this 3,000 years ago, you see the same diagram that I showed you earlier. And then I changed the horizontal scale, and I just wanted to look at the 1900 to 2000, and you see this is the plot of, in other words, the last 127 years, this is the plot of the temperature. Okay? Now what we do is to, and the increase in temperature since 1760 is much faster than it has ever occurred before. We grew by about 75 degrees, 0.75 degrees, and there is not. Now, if I go to the next one, I have a similar diagram, but this time for CO2, and here you have the same structure, and then you look at the data just from almost 2,000 years, and it's almost flat, and 1750s here, and look what happens to the temperature. This is a separate plot, a different scale. These are beautiful measurements in Mauna Loa in Hawaii by a scientist that liked to take good measurements of CO2 long before CO2 became an issue. And as a result, we now have this beautiful, CO2 oscillates as a function of time with a near periodicity, because depending upon the season, you have more CO2 absorbed by plants and others than you do have in other period of the year. But this is the plot of CO2 in the last 400,000 years. And it gives you this spike that begins when the Industrial Revolution began. Now, if you still don't believe it, and I'm not suggesting that you don't believe it, you have another plot, which in the same slide, from top to bottom, you have population in billions. Unfortunately, we are growing fast too. We have carbon dioxide, the second line. We have NO2, the third. We have methane, which, by the way, is a very effective trace gas. And then finally, at the bottom, we have the temperature, with error bars that cover this bright area. You don't quite see it, I barely see it also here, is if you look at the temperature since 17 something, you see that there are two diagrams there, and one of which is actually a period where the measurements were very accurate, because some time back temperature were either inferred, as I described to you, through the ice cores, but now since that time we have temperature working well, and so in some sense it confirms that what was reconstructed with other means is consistent with the measurement. Now, you still don't believe that? That's fine. I'm plotting, I have 3 diagrams here. The first one is this one, and what is consistent and the same for each of these plot is the observed temperature, is the red trace. The red trace is the same in all 3 panels. In the first panel, we only put in, to reproduce the data, solar variability and volcanic activity. And you get this. Not a good match with the observations. In the second panel, we are intentionally trying to reproduce the observations, the red line, by putting into the system just greenhouse gases and aerosols, these small particles that come out of combustion. You are doing better, but not quite well. And you are doing much better in the third panel, when not only you put in what you did in the other 2 panels, but in addition you also account for variations of the surface, variation of vegetation, forest, etc., i.e. what we refer to as, so to speak, human activities, because it's us who have the forest. And I think it's clear that the matching is indeed, I say quite good, but in addition is much better than in any of the other 2 cases. And here you have a diagram that was done by Jim Henson, in which you quantify the contributions of the various trace gases to warming. And in the case of the aerosols, they can some cooling, because aerosols reflect a lot, and also they modify clouds. How will climate evolve? Not easy, very difficult question. Why? Because there are processes in the atmosphere and the ocean that are tricky, and we do not know necessarily, in fact, we don't know how to predict them. And we call them the positive or negative feedback. You do something to the atmosphere, and the atmosphere reacts as to increase what you do. There is an initial change that you produce, and the Earth reacts to it by making that change even bigger. That's the positive feedback. And the negative feedback is the opposite. And then the tipping points are defined as configurations of the Earth system that if you reach it, things happen that you will not be able to change. The change will be absolutely unstoppable. That's what we refer to as tipping points, and I will give you an example. 10 minutes? Wow, it's a lot of time. And so we have these feedbacks, some of which take place very quickly. If you alter the amount of water vapor in the atmosphere, you know it. It starts getting warm, precipitation changes, clouds form that otherwise wouldn't. These are feedbacks that are relatively rapid. But then there are very slow feedbacks that take place over centuries. Ice sheets is one example. Deforestation is another, because they're just taking place over a long period of time. That's another complication. You have these feedback processes, and some of which react quickly, others take a long time to react. Life is not easy in the Earth system. It's a challenge for scientists, but it's simply a complicated system. Example here. Look at this example. I'm referring to the water vapor feedback. The temperature increases, make that assumption. And if it increases, the system warms up, moisture from the ground evaporates, water vapor evaporates from the sea, more water vapor takes place. Then you can choose to follow 2 different paths. More water vapor content, okay, the temperature increases. I mentioned it to you earlier. if you evaporate more water vapor, the water vapor will act. There will be water vapor. It doesn't have to be condensed into a cloud. There will be water vapor in the atmosphere, and the water vapor is a very powerful trace gas. On the other hand, and then you go to the right, more cloud, you may have, more water vapor means that you will have more clouds. And as I told you, clouds reflect energy. And if they reflect energy, it means they reduce the temperature. They reduce the temperature below the cloud because the solar energy is reflected. So you started from a temperature increase and you ended up in one case with further increases in temperature. In the other case, you end up with temperature decreases. That's the simplest example I can give you of how life is not simple in the Earth. Okay? And of course, it's why scientists love these challenges. They can't solve the problem, but nevertheless, we like to solve it. The temperature is today, I'm about to give you the most worrisome example in my view. The temperature that we have today, the distribution in terms of latitude, longitude, equator and poles, is the result of atmospheric processes with the jet streams that you know what they are, they can move around, and surely they play a major role in the distribution of temperature in the atmosphere. The equivalent of the jet streams are the ocean currents that you see depicted in this slide. The yellow, the reddish area are the surface currents in the ocean that are part of bringing the temperature, affecting the distribution between the equators and the north and the south. So here you have measurements and theory, the distribution as a function of longitude and latitude of these surface currents which are warm and the bottom of the sea currents that are the blue one which are cold. Now here you also have depicted, if you like, the various processes that I already mentioned before, including volcanic explosion, trees, etc., clouds that are affecting the air. But let's look at what happens here. The current comes in and it's at the surface and it has to go down to close the loop. I mean, you have to close this loop if in this region, if in fact the loop structure that you have is what it is. This is another cross-section of the same loop I show you. So here it is, the warm current coming here, and somehow is dense enough, there is enough salt in it, that it goes down and begins the loop at the bottom of the sea. Let me repeat, surface current reaches this region, is dense because has a certain density because of salinity, and it sinks down and it closes the loop. Now imagine that they were warm. These are ice, these immense ice sheets in the Arctic region. This is all ice. But we are warming the system. We are causing this ice to melt. And look at this, and look at this. You see this area here? Is the area, this is only a picture, okay? Is the area where the ice has been melting. Means basically fresh water, basically water without salt, that suddenly melts on the ocean, which has a certain amount of salinity. It reduces the salinity because you add fresh water, unsalty water on salty water, so the salinity gets reduced. The weight of the water is reduced. The ability of the water to sink is reduced. And so what you may end up, it doesn't happen, what you may end up is this is a process which could lead to a disruption right in this region of the general ocean circulation. And if you do that, you may very well have reached a tipping point that once that process has taken place, you will not be able to stop it. I'm not telling you it's going to happen tomorrow, etc., but I'm saying that this is a realistic This is something that one should recognize is possible. And it's what we call a tipping point. Other tipping point could be the further melting of the ice sheets in Greenland or in Antarctica. And in fact, we have some evidence that the West Antarctic ice sheet is beginning to collapse. We may have the beginning of major permafrost thawing, because the ground in this very cold region has a lot of methane, because the entire ground is actually frozen. But as the temperature increases, that ground may cease to be frozen, and when that happens, the methane, which is trapped into that ground, evaporates into the atmosphere, causing further increase. Human nature. Look, this is the transition that I mentioned to you earlier. 100,000 years of difference. Fast, it increases, the temperature goes fast. This is basically the same picture that I said earlier. This is the incoming solar radiation. The beginning of these periodic oscillations of 100,000, probably the beginning is variations in the incoming solar radiation of the order of 0.25 watts per meter square. Then you have the reaction of the greenhouse gases, which is probably going to add 3 watts per meter square. You have additional 3 watts per meter square due to changes in vegetation on albedo. And if you sum up all these effects, A, B, and C, which are causing warming, you end up with a total amount which is of the order of 7, I didn't write the number, but if you sum up these 3 numbers, you end up with a 675 watts per meter square. Natural processes add heat in these major changes of the order of 7 watts per meter square. Think of that now. What we have done since the beginning of the Industrial Revolution, it has been to add 1.5 watts per meter square. So there are 2 things I want us to reflect upon. 1, 1.5 is smaller than 7, but it's not infinitesimal with respect to 7. In our way of looking at things, 1.5 is of the same order of magnitude as 7. Point number 1. Point number 2. We did this 7 over 10,000 years. 10,000 years. We have added 7.5 watts per meter square over a period of 10,000 years. We have added 1.5 over the period of 200 or so years. 10,000 versus 200. And that is what I think we should reflect very carefully on. We have added, I'm repeating myself, we added this heat over a period of time, short, compared to the period of time over which nature has added heat and justifies these oscillations that we have had over time. And this is a picture, the depiction of the same thing I just said. 1.5 here, between 1750 and 1950, and then an additional 1 to between until 1010. And this is and this was done in 10,000 years, and this was done since 1750. So the question remains. We cannot really answer it, but can the small forces that we have been dealing with alter this human activity? Can alter the changes that have occurred in the past or not? And important factors that are influencing climate change. Population growth. That's a fact. I mean, clearly there is a relation with the population. Economic growth, because the amount of energy that we use, the amount of CO2 that we produce, depends of people around the world. And as I said earlier, a question of fairness begins to take, because we cannot and should not ask poor countries or developing countries to do things differently than we did. and to take advantage of energy sources even though they produce CO2. And then there is an interesting possibility, and that is the technology options. Because we may have the opportunity of developing technology, creating new jobs, the politician would say, which is true, such as increasing the efficiency of the energy use, using alternative sources of energy, renewable, solar, wind, biomass, nuclear fusion, that many of us don't like, but France, for example, the majority of the energy in France comes from nuclear fusion. These are all things that can influence climate, and carbon sequestration, the reduction of CO2, NO2, agriculture and water usage can make a big difference. The way we use fertilizer in agriculture can make a big difference. Pesticides can make a hell of a difference. Water conservation policies can make a big difference. Now, with respect to the future, I'd like to make one point. That we do not talk about prediction about climate as we do about weather. We talk about projections. We make certain assumptions about use of energy. Scenario 1, scenario 2, scenario 3. Highly arbitrary, not irrational. And it is with that assumption, this will be the amount of energy that will be used, that we project what the climate will be. Project what the climate will be, not forecast what the climate will be. Because a forecast implies, this is the initial state, let's see what happens tomorrow. You solve the equations given that initial state, and you see what happens. Projections means we anticipate the amount of energy that will be used today, tomorrow, the day after tomorrow. We make that assumption, and then having made that assumption, we say, if that is what we will do, then the climate will look like a certain way. These are projections. A possible example of climate change. This is a reproduction, a numerical reproduction. This is what a meter of sea level rise will do to Florida. The red pieces will go under. And I spare the few graphs corresponding to 6 meters of water. This is what will happen, or is estimated to happen, if sea level rises by half or 1 meter in areas such as Bangladesh, India, Indonesia, Japan, areas which are low, where the water, the sea level increase can be very, unfortunately, very effective. And you can have substantial portions of their land go underwater. Look at Bangladesh. Look at Vietnam. So these are estimates of the consequences that one can have. Fundamental concern that we should have. The temperature has never increased so much as in the last 150 years. The forcing that we've done in 200 and some years on 1.5 is larger than the amount of forcing that was done to go from one for initiating changes of the big 100,000 oscillations. Well, I already said that the increase in temperature is unprecedented. And CO2, we never had values of CO2 as large as we have today in the last 500,000 years. We just never had them. So, who knows, we don't have paleoclimate data that can tell us what was happening. Glacier and ice sheets respond more quickly than anticipated, by far. The sea ice is declining faster than anticipated. And the positive feedbacks could bring the Earth system towards this tipping point I described to you with Samson. There are these two pictures of two gentlemen that were the one that measured CO2, that beautiful curve, almost perfect sinusoid. And I like to point this out. The top guy, excuse me, I misspoke. The top guy is Svante Arrhenius, who in 1896, where the issue was not political, nothing, he did observe and carried out an experiment and made the observation. Maybe it was the first one that made the observations that trace gases, these gases such as CO2 in the atmosphere, could warm the climate. And since he was from Sweden, he said that's not bad, because it means that we will be able to cultivate better and the vegetation will be better. So he was happy. He pointed out that this was happening. Point number 2. This guy, Roger Revelle, is the one that conceived these measurements that I show you. And he made a statement that you can read, but I read it for you as well, that human beings are now carrying out a large-scale geophysical experiment of a kind that could not have happened in the past, people weren't there, nor be reproduced in the future. We are carrying out an experiment, and as such, by definition, if you like, experiments are not a priori, produce results that are not a priori known, otherwise they would not be an experiment. This is a beautiful picture, and I like to end with this beautiful picture. I have other things, but the time's up. Thank you.
So we'll open the floor for questions on either the talk or else any of the work that Dr. Einaudi's done with NASA or his studies.
Yes?
Dr. Einaudi, what would you predict? And I realize this is a very difficult question. What is the weather going to be like 1,000 years from now?
I thought I demonstrated to you that I will not do that. I don't know the answer. What I do know is that what we are doing today is going to affect the temperature for centuries. We have some evidence that the jet streams, the temperature gradients between between the poles and the equator are varying. If that happens, the jet streams are changing position, maybe slightly, and if the jet streams change, they affect the weather as in a major way. So one would accept possibly stronger floods, heat waves, and so on. But I say may, and I'd rather do that than be uncertain that it will happen to avoid it. That's the way I feel. But there can be effects, yes. Otherwise we wouldn't work too much.
How do you see us changing the trajectory that we're on?
Very difficult. Very difficult. Because it's easier to consume more energy than less. It's you would need to change your habits. You would need to turn off the lights when you don't need them. You would need to change many agricultural processes. There is a difficulties there is a major difficulty of predicting the cost of doing something specifically. The cap and trade, this process of taxing carbon, which is what Jim Hansen would suggest to do. It's very difficult to make specific cost analysis. It's just when it involves changes of habit, difficult to bring about, because we're all, how should I say, we like our habits. And furthermore, in general, Americans, and not just Americans, in the past, when something drastic took place, such as Pearl Harbor attack by the Japanese, or Katrina, people converged in a solution. They decided to act quickly. Whether they liked or they supported the war in Vietnam, World War II, in that case, regardless of their political view, they supported intervention immediately. it was an event, it took place, and the reaction was instantaneous. Here we are talking about a process that is lengthy, that takes place over a long period of time. And we all, politicians, have a time span of 2 years or 6 years. And in general, the public, it's not going to affect my life. And whether they affect the next generations, I'm sorry, is not necessarily up in their mind. And that's your life. Yes? Sorry?
Early on in the lecture, you talked about how politics come in with implementation of laws for climate change.
Yes.
And climate change has been completely ignored in this election.
Yes, it is.
I was just wondering if you have any estimates as to when the United States might take
My take, I'm sorry?
When do you think the United States might take some action on this?
I don't know. I don't know. I can say that with respect to this problem, the attitude in other parts of the world is a bit better. You have a much smaller number of skeptics in Europe than you do here. So I really don't have the answer. My hope is that once the elections are done, I mean, let's face it, any attempt to bring about changes on this issue were not approved by either Congress or the Senate or both. Now, once the politics issues are over, maybe they're willing to take another look and make different decisions. But I would hate to predict because let's leave it at that. Yes.
You spoke earlier about the jet streams and
yes.
potential tipping points. My question is about desalination processes and technologies that nations and companies are working on. Do you see any rebound effects if the country implements desalination?
Desalination, you mean to have more water drinkable? Is that what you mean?
Right, yes.
I don't know. I never addressed that issue, and I never read about this issue becoming so large as to affect things. So my gut reaction would say probably it would take a lot of desalination before affecting, but I don't know. Yes. You had the question, right? Yes.
How far we are to understand the climate variability at decadal timescale?
I think we need more data, and that goes with respect also to the 2 or 3 years. We're getting to a decadal El Nino and La Nina are shorter, but not for the moment. Those changes don't seem to have implied major issues or something that would be very important at this moment to know in detail. There are many other issues that are affecting what is happening because, well, for example, technology. I mean, technology development should start today. Shouldn't wait 10 years to do it. Regardless of the changes in the next 10 years. When you get into too short time scales, it becomes a little bit more questionable related those to climate change. Okay, I mean a typical minimal time over which you should define climate is 30 years, and it's the minimum. In other words, if you average over 30 years, then you can begin to talk about climate, and therefore climate changes. When you go down to 10, it becomes more questionable to talk about climate. Am I making? You need to average over a sufficiently long time to define climate, because remember, climate is an average. And typical people would say you need sufficient time to do that. Although some people would go there. I mean, of course, you're talking about climate in terms of seasons, for example, and you have to take averages over 30 years. But it's not exactly long-term climate that we're talking about.